Well, thank you very much once again for the introduction and including me in today's discussions. I really would like to thank UNISEC as well as Professors Chalabi and Aslan for really thinking of me, including me here. Also the co-speaker and everyone else on online today to take the time to talk about the topic. It's something I'm quite passionate about on how to really make the best out of the resources coming out of academia, mostly around the workforce, but many other things as well, which really shape the companies we are working in today. As I already said, I am the CEO of Mynaric, an optical communications company, doing optical communications terminals for different satellite missions. But to talk a little bit about my history, I'm a graduate of the Technical University of Munich in computer science, and then Stanford University in aerospace, which led me to a career that started in 2004 over at SpaceX, where I became the vice president in charge of avionics, guidance, navigation, control, and software. And I've got to work on all the rockets and capsules, and then the satellites of the SpaceX mission as one of the main architects. Lastly, as a vice president in charge of the mission assurance for the Starlink program. I also held roles within Airbus Defence and Space as the head of innovation and digital transformation, as well as some startup work. Just recently, I have moved on from SpaceX to become an investor myself. I invest into space companies in Europe, so I definitely have an opinion of what they should be looking out of academia as well, and I let that flow into my mind every time, and I do that actively today as a venture capitalist in Alpine Space Ventures, a European space fund, but I still keep active by being the CEO of Mynaric. From Mynaric on to, from myself onto the company that I get to lead today, which is Mynaric, which is doing optical comms. It may not be a very immediately apparent topic for many, but it is a topic that has been around for quite a long period, which was to network satellites with each other to build mesh networks in the sky. And Mynaric is a company that exactly builds components and terminals for that purpose. Today, Mynaric builds equipment for aircraft, satellites, space stations, and ground stations, and alike, and very soon mobility platforms as well, that allow you to move data between all different types of satellites to communicate in very high speed over very long distances, doing today marketing our terminals at 100 gigabits a second and working already on terabit a second in comparison with an RF system that for the same amount of power and space could only get just a few megabits a second on these distances. So overall, it is definitely a leap that we are doing today. And if you look at the current environment in space, this is exactly the backbone that builds today's mega constellation push. We have, as I said, airplane terminals. Our Hawk terminal is the one that we do for airplane, which definitely is unique for Mynaric. Not too many people do airplane terminals because of the atmospheric effects you see in lasers. And then we have the Condor terminal, which is our space terminal. Now it's in its version 3, and mostly right now being utilized for many different satellite constellations. Quite a few actually also in the defense realm used by the US DoD in different environments such as DARPA or the Space Development Agency and such. Just to give very quick numbers again, we can do with these terminals about 100 gigabits. We consume less than 60 watts, and we bridge distances of 8,000 kilometers. So if you think the fact that this is a laser pointer and the target is about 8 centimeters big, hitting an 8 centimeter target from 8,000 kilometers away with a laser beam, while 2 satellites are moving at 28,000 kilometers an hour, it's definitely a fun job to be working on. What really sets us apart is our very big focus on the technology that really makes the terminals also very cost-effective and scalable. And I'm telling all of this because I think all of this goes towards what we are looking for academia. We do a lot of research, a lot of investment, and a lot of our capital goes towards mass production, scalability, cost reduction as such. We build all metal telescopes that are made from aluminum, something that is quite difficult to do in the space environment. You can think about the thermal environment that a optical terminal goes to, that is exposed to the exterior of the satellite, and what kind of a radiative environment we have to work in. And doing that with the cheapest material we could find was definitely very, very difficult. And this is something I always repeat. Cost effective is very expensive. What I mean by that is we spend a lot of money, we spend a lot of time. This telescope took us 6 years to perfect, and it took us a lot of time to get cost effective, to get cheap. This is something our customers need. They are supposed to be built in the thousands a year, and that is as much research as any other research to bring the cost point of space down. That is very much in our portfolio. Other things we do, of course, is we work on faster and faster communication. Terabit is our next design. A terabit over a single optical channel is already a challenge already on terra firma. In space, it's even more of a challenge. And we work constantly on ultra-sensitive receiver technologies that allow for us to bring down the power consumption and increase the link distance for our customers as well. We have in-house capabilities from anywhere from the clean room to the testing capabilities that you would see to the very specific optical metrology equipment. And it may be a little bit my SpaceX blood that runs in my veins every now and then, but we are quite vertically integrated. We are not 100% religious like SpaceX in vertical integration, but we definitely look into vertical integration as an asset for the company that can really allow optical communications to reach mass market and everyone. To give a little bit of an overview of how big the company is, we are outdated slide, sorry about that. We are 250 people. That 220 was only 1.5 months ago, so you can see how fast we're growing. Most of that is in the headquarters in Munich, but we also have offices in Los Angeles with about 30 people, and in Washington, D.C., we have a handful of people who are mostly working on our government relations with the US government. On the leadership side, I'd like to point out that we are a space company, but very often we look for experience outside of the space industry as well. And a really good example for that is, for example, our COO in charge of our production, our logistics, and our quality. And he himself, when we were looking to build optical instruments in the thousands a year, we hired him out of a company, ARI, here in Munich, specializing in movie camera equipment that makes high-end optics in the thousands. And that kind of experience was very interesting for us to find outside of the space industry, because normally when you go into a room full of space specialists and you talk about building anything in the thousands a year, and you get laughed out of the room. And for him, those numbers are probably a little bit more realistic, if not a little bit low. So let's move on to the second side of the things. What are we looking for? From the Mynaric's perspective, what is the important 3 pillars that we are looking for when working with academia? I think we are, as you can imagine, we are very much interested in future technologies, in working what could be next. And future technologies don't have to be always in the area of, hey, what do we do in terms of more capability? Very often, future technology is also about miniaturization, cost optimization, and whatnot. And I'll go into that a little bit more in detail. We're looking for a very specific workforce as well. And one I highlight is a hands-on experience I would like to go on a little bit more. And the kind of mindset we need from people, what we're really looking for. I'd like to go into that in depth. And then we are looking for entrepreneurship and spin-offs. I think we're realizing that more and more innovation is coming out of small companies being formed by around an idea that in itself is so risky that large companies cannot afford to try and fail. So it's really interesting for anyone coming out of academia to take our spark and make it into a risky endeavor, get it maybe even venture backed. That's what I do most of the time. And then get it to be a technology that's available for the whole industry. And we have seen more and more technology enter the whole space realm exactly out of that chain. So on the future technologies, I'd like to be a little bit more specific. What is Mynaric looking for? And these are maybe things that you can pick up on topics that you say, okay, you know what? This is exactly something we work in today. High-speed research. We're today working on terabit. We are using coherent technology. As you can imagine, the space industry does not have the budgets to actually develop the base technology. You have some amazing companies out in the world, in the fiber optics world, that have budgets that the space industry can only dream of, that build chips today, DSPs and whatnot, that do these in the only way that can be done, all the way down in the ASIC with amazing capabilities and coherent capabilities. We need to take that to terabit and above. And there is definitely quite a bit of research in the modulation schemes in fiber, and doing this on an open optical channel, not just in two different fiber optic cables. There is research to be done there. And to be fair, we're talking about cutting edge technology, the absolute best when it comes in silicon. And when you do that and you put on top of it the idea of radiation resistance, things get very interesting and very difficult. Very often we are limited by where we can use the terrestrial technology in space. The Achilles heel is very much the radiation capability of these chips, and getting terabit class chips in radiation resistant, or at least radiation tolerant capabilities is the absolute pinnacle of what we need to be able to offer this to our companies. High precision optics have been around a lot. Today, if you look at I got to see it before it got launched. I got to visit Northrop Grumman and see it in person. I got to see James Webb Space Telescope, and oh man, that's some amazing optics. It's amazing optics because it's probably built out of $100 bills, the size of the clean room that it was in. It's expensive, and I respect and I expect that. Yet, when you talk about mass production, that is not the class of optics we can use. We need to find ways in serial production of high precision optics that allows a telescope to be built in a matter of tens of minutes and be polished and done with it. So what you need to do is leave behind the comfortable materials that we all like to use, from silicon carbides to ceramics and whatnot, and look for the aluminums of the world to see how we can do it fast, how we can do it mass producible and make it cheap. So, and that in the area of optics is a very difficult thing when you're trying to achieve wavefront qualities that are unprecedented. But it doesn't just stop there. And I'm going to come into this cost point over and over again. Cost reduction technologies are a big deal. Technology in itself, if it's not affordable, doesn't actually exist. That's the way I think about it. If only one person or one thing can afford it, that technology has limited use. Cost reduction makes technology real. It puts it into the place where it needs to go. We all know that supercomputers of yesteryear, it's the PC that made the technology go to where it needed to be. And then very specifically, we always look for capabilities in optical, anything in optoelectrical. And when it especially comes to amplifications and whatnot, we are always interested in capabilities that go into increasing our optical output without increasing the power input from the satellite. So any research into amplification of optical power in a fiber is always interesting for us. Let's come to the workforce that can make that happen. And I think academia plays a very big role in that. And I got to see the academia from two sides of the Atlantic. I got to experience it in Germany. I got to experience it in the US. And one of the most interesting things I saw was, and I was very happy to see Professor Aslan's 6 CubeSat in orbit. I think that's a tremendous experience. 20 years ago, that's exactly what I got to do as well. When I got into Stanford, I had this crazy professor, Professor Twiggs. I love him to death. He told me, hey, Bülent, I have this insane idea of building 10 by 10 by 10 satellites. We should start doing this. Together, they were doing it with Cal Poly together, and that became a standard. And what that did to the space industry is amazing. Today, I don't see very few students coming out of academia without any hands-on engineering, having built a satellite. And I can tell you, today when I open up a resume, the first thing I look for is not your grade, not your degree, not your anything. It's the first thing I look for is, what did you do? What did you actually build? How did you apply the knowledge that you gathered? If you all you did is gather knowledge in your head, but you never learned how to apply it, that's in itself very difficult for me to judge, to say if really that engine can bring the horsepower onto the road. When the rubber hits the road, that's when you prove yourself. And when I look into that, that really is the place that where really we teach people how to work in the industry, how to work in the areas outside of academia. Hands-on engineering very often comes with three interesting concepts, or at least a few of these interesting concepts. One of them is cost targets. Today, we are looking into hands-on engineering capabilities like CubeSats and whatnot that require you to be working within a limited budget. And hitting cost targets while still adhering to schedule is a capability that our workforce needs to understand from day one. It's not something that just the workplace and the management can teach. It has to be taught in schools, and that's very much taught during the hands-on engineering process. Working in iterative, agile, and innovative ways. It is difficult. I think academia needs to teach the linear solution methodology always. And I think that's a very important capability to have. Problem, analysis, solution. Yet, when you are in a difficult engineering domain, going for the cutting edge, we need to get out of that mindset and into the iterative, agile, innovative ways as well. What do I mean by that? We have, and I will comment about this again, very often the idea is like, we will find the problem statement, design something, and make it work in the first place. And very often, we are dealing in the space domain with a large amount of unknown unknowns, things we do not know this problem and don't even know the solution for yet. And only in an iterative way do you get to realize how to really build something. In SpaceX, we took that to the extreme, saying we will fly really risky first rocket when we first launched Falcon 1. And we lost three rockets until we really realized how rockets work. Other rockets, by the way, who are built in a first time right, or in a failure is not an option methodology, also almost always fail their first flight. So you can see that the iterative process comes back to you, whatever you do. So I really teach the fastest to right methodology, which comes always from an iterative method. Something we probably don't teach in the space engineering side very often, and that's something we should probably go more and more into detail as the world is getting to constellations, is serial manufacturability. What makes a design, what makes a certain engineering much easier to serially manufacture. Today, when you go to a regular mechanical engineering school and your path is supposed to take you towards car manufacturability, they don't just tell you how to design a car. They tell you how to manufacture a car. And you learn how to really combine one with the other. That is not taught today in the aerospace curriculum, but it has to become a part of it. Today, I can tell you, every single large serial manufacturing company in the space sector hires car engineers, automotive engineers. Why is that? Because in the aerospace world, we are not taught how to do this. This is a big one. And then once again, harping on the hands-on engineering side, I really, really like what is happening, I think, between universities, between institutions in a global scale. I really like very high stress, low budget, quick turnaround, big competitions like the DARPA Challenge, Hyperloop competition, Formula SAE. These are large projects that are very multidisciplinary, that are longish term, that really get people innovative. And there is a competitive factor to it that is the same that exists in the commercial world as well. Competition is built into us. So I really welcome that. Spinning off an entrepreneurship. We need to teach beyond academics also entrepreneurship, taking our engineering, making a business case out of it. We need to build a connection between technology and that business case. And interestingly, that was something I saw in Stanford that was very interesting, was they teach entrepreneurship in the Graduate School of Business of Stanford. And in one of their classes, they tell them to go out and into the other faculties and whatnot, come out with a spark, come out with a business case, come out with an innovation, and go ahead and pitch their idea in front of a bunch of VCs. And by the way, a lot of the companies came out of it as well. And interestingly, that most of us engineers never talk to the business school guys ever. It really pushes that, and it's really, it does bear a lot of fruit. We also need to start teaching about risk-taking appetite, how to take properly risk, because a risk-free execution for a company is a failure. If you're not taking any risks, you cannot be successful. But taking the risk the right way, managing that risk, and how to mitigate it along the path, and at what level to take it is very important. Once again, we have been an industry that has been, I want to say, a victim of the first lessons we learned when a fantastic person, Gene Kranz, said the words, failure is not an option. But that word said for a specific time and a specific thing about a loss of life has become the motto of the industry, which became never make failures. And that is not okay. We need to start making more failures. An industry that doesn't have any failures, any setbacks, is one that doesn't innovate. So we need to try things, and we need to instill in our workforce and in our people and in our academia that failure mechanism. What I would like to also see is, let's go ahead and go from a use case back. I think this goes into entrepreneurship. Don't just define a technical requirement and let your students or let your academia try to solve it. Go from the use case of the customer. Try to make them come up with the final tech solution that solves the use case. Don't abbreviate what happens with the final step, with the final end of the value chain. If we do that, then we are taking away. We're making a soccer team that passes the ball around but never scores a goal. And most importantly, go ahead and encourage entrepreneurship. Build entrepreneurship centers in the universities. I really welcome that in every university, and I've seen it happening, so I'm quite happy about it. But I want to see more of it. Here in Munich, we enjoy a very great institution called Unternehmertum, which really does that. And I see it more and more. I got to see the ones in the Technical University of Istanbul and in METU as well. I was quite impressed also. And yes, we need to build more of that. Universities are going to become hubs. And if you look at some of these leading entrepreneurial universities, you have the university in the middle and a tremendous amount of infrastructure and all this technology happening just around it geographically. And in the West Coast or in San Francisco, they call that Silicon Valley. So let's go ahead and build more of these. I definitely would welcome that. But enough from me. I thank you all. I thank you for giving me the time. I hope I didn't go too much over my time, and I appreciate you listening to me. Thanks.
Okay, Bülent, thank you very much for a great talk. I think you were very much on time, and we can even have one or two quick questions. Well, I can, but I will let someone else to ask a question. Please go ahead. No questions? Well, then let me ask the question about the laser communication needing no license currently. What will be the future for that?
I think so far, every conversation with the ITU and the FCC tells us that they are not looking into licensing it at all. The reason for ITU, and let's face it, ITU is one of the biggest bureaucracies, but a very necessary bureaucracy, is the fact that the world of radio communication is filled with violators and victims, and you need to coordinate that. And even the best radio technology has side lobes, it goes everywhere. And that's the biggest advantage of optical comms. It's a point-to-point, physically point-to-point communication. And you don't have these types of problems. So it's a victim-free communication as long as I don't shine it right into your aperture as well, which is very tough to do if you're not cooperating. So I think we're going to live in a license-free optical comms world for quite some time.
Okay, then we have another question. Ilyas from Sharjah, he asks, what type of detector technology are you using?
Multiple, depending on the application. We can be using an avalanche photodiode today. Today, given our customers, we are in the non-coherent world today, up to 10 gigabits. We do direct detection on off. And then we use, of course, also just a simple pin diode for the higher end of the spectrum, for the higher end of the bandwidth, going into an FPGA to really decode that. But today, when we are going for 100 gigabits, of course, we're going into coherent behind the pin diode. That's the easiest way to go.
Well, Bülent, thank you very, very much for your time in those busy times. It was great to have you. Okay, well, Herman has a question. Just a minute. Okay, go, Herman.
Yes, I'm more of a. Can you hear me? I'm more of a control systems engineer. So what is interesting to me is your pointing accuracy required with this laser communication, because your laser beam disperse a bit over a distance. So at what is the distance you mentioned there? 3,000 kilometers. It will disperse.
8,000, yeah.
Definitely. So what is the pointing accuracy for your laser transmitter, for example? The receiver must just be in that dispersion beam.
Absolutely. At about 8,000 kilometers, you end up with, I don't want to say too many arc seconds and arc radians and whatnot. It's a tiny, really, really very well, almost collimated beam. So it goes really, really, really in one beam. When it arrives at the target satellite, it's just a few tens of meters wide. So you're really trying to hit a perfect target. We try to keep it as narrow as possible because that just increases increases my link budget, and more photons land on my receiver side. But the receiver is about 8 centimeters, so not that big. The pointing accuracy is interesting. So we are an active system. So we actually use the incoming laser to shoot the outgoing laser. And we have an active control loop using a very fast steering mirror. And that's what every optical communication system does out there, because we have to take out the satellite motion and we have to take out the vibration. But also, there is never the perfect knowledge of the other satellite. And very often from the satellite, from the host satellite, we get the location of the other satellite in just in tenths of degrees, and that's about it. And then we have to find the communication partner. Can take us about 30, 40 seconds to do so, depending on how big the error is. But after that, we are in micro radians and pointing accuracy using our control system and the incoming signal.
Okay, Bülent, just I think there is an interesting question for students and new graduates. Let me read that. How would you, as Mynaric, be able to support a new approach to empower students to get entrepreneurial and engineering knowledge?
To be fair, I think as Mynaric, and I think with all the other things that I'm involved in, I'm looking for a challenge that one can do while in the university. I think we did that at SpaceX, and we did the Hyperloop challenge. Now they did the boring challenge. Those were really 5 amazing races, which I'm quite proud that Technical University won all 5 of them. And the Technical University of Munich, I got to mentor them. They've won quite well. I need to find something similar. Optical capabilities always require a certain amount of additional CapEx, a certain amount of additional capability. So we need to somehow summarize the difficulty of an optical link and build a challenge around it and build something around that line. And if I'm trying to do that, it's going to be an interesting thing to put together. And I'm not really sure it's going to be just around the optical link. I'm involved also in a new launcher. I'm involved in a satellite company, maybe a combo package of doing a demonstration with a price. And let's face it, when I engage students like that, some amazing people come out.
Okay,
by the way, every single
very
time.
last, very short.
Yeah, absolutely.
Have you, do you have heritage coming from European data relay system?
No, actually not. It's actually our optical communications technology has been a very German technology up until now, and the two leading companies come out of Germany. The one with actually more heritage is the one out west. Is it's a subsidiary of Airbus called TSAT, and they have been working on the high-end, really high-end optical comms for quite some time, together with the German Aerospace Research Center, and they are the terminals flying on the EDRIS system. We definitely look up to that. That's a great system. Our target has been more the mass manufactured constellation terminals, where TSAT is also beginning to be active also.
Okay, thank you, Bülent. Thank you very much for your time.